Brushless synchronous generators are both complex and critical pieces of machinery. The rotor winding insulation prevents high electrical currents produced by the exciter from flowing into destructive paths. The windings are stressed by centrifugal force, vibration, and heat. If the insulation breaks down and a ground fault goes undetected, the result is catastrophic. Hi, my name is Mike Scott, Senior Applications Engineer with Accumetrics. In this video, I'm going to outline and demonstrate our AT8000 Earth Fault Resistance Monitor for brushless generators. The system installs on the exciter and uses telemetry to continuously monitor the insulation resistance level and field excitation voltage. It provides 4 to 20 milliamp signals that are routed to the control room, as well as dual relays to alert and then alarm upon dangerously low resistance levels in the generator's rotor. The accompanying software even provides an indication of the location on the rotor at which the fault has been detected.
Here is an overview of the EFRM ground fault monitoring system for end-of-shaft applications. As you will see in a moment, the system installs on the exciter on a brushless generator in situations where space allows. We also have a mid-shaft solution that offers the same measurements and features outlined in this video, but installs at the coupling between the rotor and exciter on a brushless generator. The test leads from the bus bars on the exciter are landed on the transmitter. This part of the design spins with the rotor and exciter. We will review the installation momentarily. Next, we have the stationary pickup antenna loop, which uses telemetry to acquire the insulation resistance and field excitation voltage measurements from the exciter. The transmitter, which is bolted to the exciter, rotates around the center of the pickup antenna loop. Finally, we have the receiver enclosure. A BNC cable is used to connect the output of the pickup antenna to the input of the receiver enclosure. In our demonstration, this spinning light will trigger when the insulation resistance drops below the alert relay threshold. Turning our attention to the receiver enclosure, the alert, alarm, and malfunction relays are located here. Alert and alarm trigger when the insulation resistance level decreases and can be wired normally open or closed. The malfunction relay is normally closed. Using this logic, technicians are alerted whether the cause of the malfunction is signal loss or a complete loss of power. There is an LED light above each relay. The 4 to 20 milliamp signal output terminals are at bottom left. There is a 4 to 20 milliamp signal for both insulation resistance and field excitation voltage. These signals are of course typically routed to the PLC in the plant control room. This BNC connection is where the output of the pickup antenna is connected. Finally, there is a serial port for computer connection. We will highlight the EFRM View software in a moment. Typically, this connection is only used in diagnostic situations where there is concern about the generator rotor insulation resistance. Let us review a typical EFRM ground fault monitoring system end-of-shaft installation. You're looking at the end of a customer's generator, and this is the end cap that's covering the exciter. These 4 bolt holes are used for removal of the end cap only, otherwise they go unused, and we use those in this case to install our mounting hub. Also, as you'll see in a moment, the customer drilled a hole in the center of their end cap through which we could run our test leads. Once we remove the end cap, it exposes the bus bars on the exciter. For the bus bars, we need to drill and tap into the bus bars on the positive and negative terminal to install our test leads. The test leads come through the hole that the customer drilled in the center of their rotor end cap. And then this design here is made by Accumetrics. This is our mounting hub. And as I said, our mounting hub in this case used that bolt pattern that's used for the removal of the end cap. So we took advantage of those holes that already existed. You can see how the mounting hub bolts into place. And then the mounting holes for the transmitter are along the outside of the mounting hub. Of course, our test leads are coming through the center of the mounting hub. Finally, our transmitter is installed. Our test leads are run through holes on the transmitter itself, and then those test leads are secured to the transmitter so that we can get the signal to the pickup antenna. Finally, the pickup antenna is stationary and it's installed on a right angle mounting bracket. And of course, it goes around the transmitter. Now we need to protect the pickup antenna, so it's installed inside of a top hat design. We call it a top hat enclosure, as you see here in the final picture. And that top hat enclosure is also designed and installed by Accumetrics. And it has a right angle conduit coming out of the top hat. And the customer can connect their wiring conduit to our conduit. And of course, that signal runs to the receiver enclosure. One more look at the system. In this case, the customer's end cap looked like this, number 3 here. And the customer drilled a hole through the center of their end cap. We then installed our mounting hub, which you see here. And we ran the test leads that are connected to the bus bars through the center of the customer's end cap, then through the center of our mounting hub, and finally through the backside of the transmitter. They were landed on the transmitter. And finally, the last piece of the puzzle is the pickup antenna, which is stationary, and the signal is transmitted via telemetry as these 3 items spin, of course, to the pickup antenna and eventually to the receiver enclosure so that the customer can have a 4 to 20 milliamp signal for both insulation resistance and field excitation voltage, as well as other features.
Let's show how the system works when a ground fault on the rotor insulation resistance occurs. On the right-hand side of the screen, you're looking inside the enclosure of the EFRM monitoring system. And to the right of the enclosure, we have a spinning light that will trigger when our first alert level is crossed, our first threshold is crossed. And on the left-hand side of the screen, you see the EFRM View software. Now right now, we're simulating that the generator resistance is 1 mega ohm, which is 1 million ohms. And you can see that reflected at the top left of the screen. We're measuring 994,000 ohms, or 994 kilo ohms. And you also see it on the plot, where the plotting software is starting to draw a trend at 1 mega ohm. You can also see here in the software that we have indicators for our first alarm and second alarm. Our second alarm is actually the alert, and it's going to occur at 100,000 ohms or 100 kilo ohms. And our alarm, or alarm 1, is going to trigger at anything below 2,000 ohms, so a very low resistance level for a generator. So here at 1 mega ohm, we also have a 4 to 20 milliamp signal that is 14 milliamps. So the technicians in the control room would see 14 milliamps coming from the EFRM ground fault monitoring receiver box. Now let's drop our resistance to 100,000 ohms or 100K ohms. I'm just going to change my decade box to 100K ohms. And you can see the plot on our software start to drop. And you can also see that the alarm has triggered. This is our first alert level. Our spinny light has triggered, as well as the red light in the EFRM View monitoring software. You may have noticed it didn't trigger immediately. We had a 5-second delay, and that's due to the dwell seconds that you see here in the EFRM View software. What's actually happening, and we'll explain this again when we get to the alarm value, is the system's making 3 measurements and averaging them over a 5-second period. And if that average is lower than the threshold of 100,000 ohms, it will signal to trip the alarm. So you can consider the dwell seconds as a time delay, if you will, like we use with a lot of other measurements: pressure, strain, force, vibration, etc. You can see that the plot has dropped to 100,000 ohms. My measurement in the top left corner is just under 100,000 ohms as well. And finally, my 4 to 20 milliamp value in the control room is 12 milliamps. So my technicians know that the resistance is dropping on this generator. Finally, let's show a real serious fault condition only 1 kiloohm or 1,000 ohms of resistance. And you see the plot starting to decrease already. It dropped rapidly as we made those 3 measurements in 5 seconds. And you might have heard it. You can see inside the enclosure that the second alarm has triggered. You can also see it in the EphraimView software. Alarm number 1 triggered after that 5-second time delay where the system made sure that the resistance had dropped below the threshold by, again, making 3 measurements over a 5-second period. Also, the resistance in the top left, the actual resistance, a live resistance measurement, is about 1,000 ohms. And of course, it's reflected in our trend and reflected in our 4 to 20 milliamp signal, which is now dropped to 8 milliamps. And so that's how the Ephraim system would react in a real generator ground fault situation where the insulation resistance has broken down. As I mentioned earlier, this specific video outlines our end of shaft system, but we also have mid-shaft options that install at the coupling between the exciter and the generator rotor. For more information on all of our systems, please visit AccumetricsWithAnX.com.